Right now, more than 15 billion miles from Earth, a machine the size of a small car is drifting through the coldest, emptiest, most hostile environment ever measured by human technology. Voyager 1 crossed the final boundary of our sun's protection in 2012, and what it found on the other side should unsettle anyone who imagines humanity venturing beyond our solar system. The galactic cosmic ray count surged. The magnetic field shifted direction. The solar wind that had accompanied the spacecraft for 35 years vanished entirely. Voyager entered a realm where the sun's influence means nothing, where radiation from ancient supernovae floods every cubic centimetre, and where the nearest safe harbour is a star system over 4 light-years away. What lies beyond our solar system is not adventure, it is exposure. If you enjoy journeys into the deepest truths about our universe, hit that like button and subscribe. It means more than you know and helps bring more stories like this one to life. Now, with all that being said, get yourself comfortable. Let's begin. There is a machine out there right now, tumbling through absolute darkness. More than 15 billion miles from the warmth of the sun. It weighs less than a small car. Its main antenna is 12 feet across. Its body is roughly the size of a compact sedan, with a long boom extending outward, carrying magnetometers and a nuclear power source that is slowly, irreversibly dying. This machine was built in the 1970s using technology less powerful than the processor inside a modern musical greeting card. It was designed to study Jupiter and Saturn. It was expected to function for 5 years. It has been operating for nearly half a century, and it is still talking to us from a place no human object has ever been before. Voyager 1, launched on September 5, 1977, from Launch Complex 41 at Cape Canaveral, Florida, a Titan IIIe Centaur rocket punched it through Earth's atmosphere and set it on a trajectory toward the outer planets. Its twin, Voyager 2, had actually launched 16 days earlier, on August 20th, but on a slower path that would carry it past all 4 gas giants. Voyager 1 took a faster, more direct route, swinging past Jupiter in March of 1979 and Saturn in November of 1980. After its encounter with Saturn, Voyager 1's planetary mission was effectively over. It had photographed the Great Red Spot in detail never seen before. It had discovered active volcanoes on Jupiter's moon Io. It had studied the intricate ring system of Saturn and made the first close observations of Titan's thick orange atmosphere. But instead of shutting down, Voyager 1 kept going. There was nothing to stop it. The gravitational assist from Saturn had flung the spacecraft upward out of the plane of the planets, heading away from the Sun at roughly 38,000 miles per hour. No engine fired to slow it down. No course correction aimed it at a new destination. It simply continued along the trajectory that gravity and engineering had prescribed, moving outward, second by second, mile by mile, year after year, into regions of space where nothing human had ever ventured. Voyager 2 followed a different path but the same ultimate fate. After visiting Jupiter, Saturn, Uranus, and Neptune, completing the only grand tour of all 4 outer planets in history, Voyager 2 also headed outward. Its trajectory carried it in a different direction from its twin, angled southward relative to the plane of the solar system. By the late 1980s, both spacecraft had completed their planetary encounters and entered what NASA designated the Voyager Interstellar mission. The new objective was simple in concept and staggering in ambition. Keep flying, keep measuring, find the edge of the sun's influence, and tell us what lies beyond. The distances involved are difficult to process with a human brain. Voyager 1 currently sits approximately 163 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. Multiply that by 163. The result is over 15 billion miles. Voyager 2 trails at roughly 137 astronomical units, approximately 12.5 billion miles out. Both spacecraft continue moving outward at speeds that would cross the entire United States in about 5 minutes. But that barely register against the scale of interstellar distance. At 15 billion miles, the Sun is no longer the blazing disk that dominates our daytime sky. From Voyager 1's position, the Sun would appear as a very bright star, perhaps the brightest in its sky, but fundamentally a point of light rather than a sphere. The warmth is undetectable. The gravitational pull, while still technically present and still bending the spacecraft's path by immeasurably small amounts, has long since ceased to be the dominant influence on Voyager's daily experience. The solar wind, the stream of charged particles that has accompanied the spacecraft for its entire journey, no longer flows past its instruments. That wind ended. That is the story. Voyager 1 and Voyager 2 are the most distant human-made objects in existence. Nothing else is even close to competing. Pioneer 10 and Pioneer 11, launched in the early 1970s, preceded the Voyagers into deep space but stopped transmitting decades ago. Pioneer 10 sent its last weak signal in January of 2003. Pioneer 11 fell silent even earlier, in September of 1995. Both spacecraft are still out there, drifting, but they are mute. They carry no functioning instruments. They send no data. They have become inert metal, tumbling through the void without purpose or voice. New Horizons, the spacecraft that flew past Pluto in 2015 and later visited the Kuiper Belt object Arrokoth, remains active and is heading outward. But it sits far closer to the Sun than either Voyager, at roughly 60 astronomical units. It has not yet approached the termination shock, let alone the heliopause. It will be decades before New Horizons reaches the boundary region, and its instruments were not designed for the same measurements the Voyagers carry. In the hierarchy of human exploration, the Voyagers occupy a category that contains only themselves. They are the scouts, the first emissaries, the only machines that have physically touched the medium between the stars and reported back what they found. But to understand what they found, you first have to understand what they crossed. And this is where most public descriptions of the Voyager mission become dangerously imprecise. When news headlines declared that Voyager 1 had left the solar system, they were using a phrase that is scientifically misleading. The solar system, defined by the Sun's gravitational dominance, extends enormously farther than Voyager has travelled. The Oort cloud, a vast theoretical shell of icy bodies loosely bound to the Sun by gravity, is believed to begin at roughly 2,000 astronomical units from the Sun and extend outward to perhaps 100,000 astronomical units. Voyager 1, at 163 astronomical units, has not even reached the inner edge of this structure. At its current speed, it would take approximately 500 years to arrive at the Oort cloud's inner boundary, and roughly 30,000 years to pass through the cloud entirely. Beyond the Oort cloud, the Sun's gravitational influence continues, weakening with distance according to the inverse square law but never truly reaching zero. The gravitational sphere of influence of the Sun, the region where its pull dominates over that of neighbouring stars, extends roughly 1 to 2 light-years outward, depending on the mass and proximity of nearby stellar systems. The nearest star, Proxima Centauri, lies about 4.24 light-years away. Voyager 1 is currently less than 1 light day from Earth, which is roughly 1/365th of a light-year. It has covered less than 0.1% of the distance to the nearest star. By the definition of gravitational dominance, Voyager is still very much inside the solar system and will be for tens of thousands of years. So what did Voyager actually leave? It left the heliosphere, and this distinction is not a technicality, it is the entire point. The heliosphere is the region of space controlled by the solar wind, a continuous outflow of charged particles ejected from the Sun's corona at speeds ranging between 300 and 800 kilometers per second. This wind carries with it the Sun's magnetic field, stretched and twisted by solar rotation into a vast spiraling structure. As the wind flows outward, it inflates an enormous bubble around the Sun, pushing against the pressure of the interstellar medium, the thin gas and dust and magnetic fields that fill the space between stars. Where the outward push of the solar wind balances the inward pressure of the interstellar medium, a boundary forms. That boundary is called the heliopause. It is the outermost edge of the Sun's direct physical influence on its surrounding environment. Inside the heliopause, conditions are shaped by the Sun. The magnetic field is solar. The dominant charged particles are solar wind ions. The radiation environment is modulated by solar activity. The 11-year solar cycle governs how many cosmic rays penetrate inward, how strong the magnetic field is at various distances, and how far the solar wind extends before it decelerates. Outside the heliopause, the Sun's control ends. The magnetic field becomes galactic in origin. The particle population shifts from solar wind ions to galactic cosmic rays and interstellar plasma. The radiation environment is no longer governed by our star, but by the accumulated violence of the Milky Way. Supernova remnants, neutron star magnetospheres, and particle acceleration processes operating on scales that span thousands of light years. This is the boundary Voyager crossed, not the edge of the solar system in the gravitational sense, not the departure from the Sun's family of planets and comets and asteroids, but something arguably more significant, the edge of the Sun's protective influence, the point beyond which the Sun can no longer shield anything from the full force of the galactic environment. The crossing did not happen all at once. It happened in stages, and the story of how NASA confirmed it is one of the most painstaking detective stories in the history of space science. Voyager 1 first encountered the termination shock in December of 2004 at a distance of approximately 94 astronomical units. The termination shock is the inner boundary of the heliosphere's edge region, the point where the supersonic solar wind abruptly slows to subsonic speeds as it begins to feel the back pressure of the interstellar medium. Crossing this boundary was itself a major discovery. The distance was farther from the Sun than some models had predicted, and closer than others. The shock was not a smooth, symmetric shell, but an uneven, fluctuating surface that Voyager passed through multiple times as the boundary rippled back and forth across the spacecraft's position. Voyager 2 crossed the termination shock in August of 2007 at a distance of approximately 84 astronomical units, 10 astronomical units closer to the Sun than its twins crossing. This asymmetry revealed something important about the heliosphere's shape. It is not a perfect sphere. The heliosphere is compressed on the side facing the direction of the solar system's motion through the interstellar medium and elongated on the trailing side. The Sun and all its planets are moving through the galaxy at roughly 230 kilometers per second. The interstellar medium rams into the heliosphere from that direction, squeezing the boundary closer to the Sun on the leading side. Voyager 1 exited on the upstream side. Voyager 2 crossed on the flank. The different distances confirmed that the heliosphere is a dynamic, asymmetric structure shaped by the interaction between the solar wind and its galactic surroundings. Beyond the termination shock, both spacecraft entered the heliosheath, the thick, turbulent buffer zone where the slowed solar wind piles up, heats, and churns before reaching the heliopause. This region proved far stranger than anticipated. The magnetic field in the heliosheath was chaotic, with field lines folding back on themselves and forming magnetic bubbles that trapped and released energetic particles unpredictably. Temperatures rose to more than 100,000 Kelvin as the kinetic energy of the solar wind converted into thermal energy upon deceleration. The heliosheath was a zone of transition, neither fully solar nor fully interstellar, a no man's land where two vast physical systems pressed against each other. Then, in the summer of 2012, Voyager 1's instruments began registering the final transition. The low-energy charged particle instrument and the cosmic ray subsystem, two detectors that had been faithfully counting particles for 35 years, showed a dramatic shift. The flux of anomalous cosmic rays, particles accelerated at the termination shock within the heliosphere, dropped precipitously over just a few days. Simultaneously, the count of galactic cosmic rays, high-energy particles from outside the solar system, surged upward. The crossover was stark. The solar particle population vanished. The galactic population arrived. The sun's contribution to the local particle environment dropped to essentially zero, but the magnetic field data complicated the picture. Scientists had expected that crossing the heliopause would produce a sharp rotation in the magnetic field direction, a clean switch from the solar field orientation to the interstellar field orientation. Instead, the field direction changed gradually, over a period of days to weeks. Some researchers argued this meant Voyager had entered a new, unexpected transition region, not quite inside the heliosphere, but not truly in interstellar space either. Others argued the spacecraft had crossed the heliopause, but that the boundary was more complex than simple models predicted. The debate played out in journals and at conferences throughout 2012 and into 2013. The resolution came from an unexpected source: plasma oscillations. In early 2012, a powerful coronal mass ejection erupted from the Sun. This massive burst of solar plasma and magnetic field raced outward through the heliosphere at speeds exceeding 1,000 kilometers per second. Months later, the shockwave from this eruption reached Voyager 1's location, more than 120 astronomical units from the Sun. When the shockwave arrived, it caused the plasma surrounding the spacecraft to vibrate at specific frequencies. Voyager 1's plasma wave science instrument, one of the few instruments still receiving enough power to operate, detected these oscillations clearly. The frequency of plasma oscillations depends directly on the density of the surrounding material. Higher density produces higher frequency. When scientists analyzed the oscillation data, they calculated a plasma density of approximately 0.08 electrons per cubic centimeter. This was roughly 40 times denser than the plasma density in the outer heliosheath. The measurement was decisive. Voyager 1 was immersed in material far too dense to be solar wind plasma. It was surrounded by the interstellar medium. Working backward through the particle data, the magnetic field records, and the plasma wave measurements, scientists pinpointed the crossing. Voyager 1 had passed through the heliopause on or around August 25th. 2012, at a distance of approximately 121.7 astronomical units from the Sun. The announcement came in September of 2013, more than a year after the actual event. For those 13 months, Voyager 1 had been in interstellar space, and no one on Earth had been certain. Voyager 2 confirmed and expanded the discovery 6 years later. On November 5th, 2018, at a distance of approximately 119 astronomical units, Voyager 2 crossed the heliopause in a different direction. Its crossing was in some ways even more scientifically valuable than its twins. Voyager 2 still carried a functioning plasma science instrument, the PLS, which directly measures the properties of charged particles in the surrounding medium. Voyager 1's equivalent instrument had failed in 1980, nearly 4 decades before the heliopause crossing. Everything Voyager 1 knew about the plasma around it had to be inferred indirectly from plasma wave oscillations. Voyager 2 could measure the plasma directly, providing density, temperature, speed, and composition data that Voyager 1 simply could not. The PLS confirmed what the plasma wave data had suggested. At the heliopause, the solar wind plasma disappeared abruptly. One moment, Voyager 2 was immersed in outward-flowing solar material. The next, that flow had ceased entirely, and the spacecraft was surrounded by a denser, hotter, and essentially stationary plasma of interstellar origin. The transition was sharp. The contrast between the two environments was unambiguous. 2 spacecraft, 2 independent crossings, 2 complete sets of instruments recording the same fundamental transition from different directions and at different times. The scientific case was airtight. The heliosphere has a definable outer boundary. That boundary can be crossed, and beyond it lies a physical environment that is measurably, fundamentally different from everything within the Sun's domain. These machines are old. Their power sources are decaying at a rate dictated by the 87.7-year half-life of plutonium-238. Each Voyager's 3 radioisotope thermoelectric generators produced about 470 watts of electrical power at launch. Today, they produce roughly 220 watts, and that number drops by approximately 4 watts every year. NASA has been systematically shutting down instruments and heaters to conserve what little power remains. The cameras were turned off in 1990. Science instruments have been deactivated one by one. Thruster firings to maintain antenna pointing toward Earth have become less frequent and less reliable as the hydrazine fuel ages and the thruster valves stiffen. The radio signals reaching Earth from Voyager 1 carry a power of roughly 23 watts at the source, transmitted through a 12-foot dish antenna aimed at a planet more than 15 billion miles away. By the time those signals reach the 70-meter dishes of NASA's Deep Space Network, the received power has fallen to roughly 1/10 billionth of a trillionth of a watt. That engineers can extract meaningful scientific data from a signal this feeble is a testament to decades of refinement in deep space communication techniques. But even this capability has limits. The round-trip light time for communicating with Voyager 1 now exceeds 45 hours. A command sent from Earth takes nearly 23 hours to arrive. The spacecraft's response takes another 23 hours to return. A single exchange requires nearly 2 full days of waiting. Within the next few years, sometime in the late 2020s or early 2030s, the power will no longer sustain any science instrument. The last heater will shut down. The last data stream will go silent. Voyager 1 and Voyager 2 will become inert objects, still racing outward at their current speeds, still carrying their instruments and their golden records, but no longer capable of sensing or reporting their environment. They will become artifacts, drifting through the interstellar medium on trajectories that will carry them past distant stars over the coming tens of thousands of years. Voyager 1 will approach within about 1.6 light-years of the star, Gliese 445 in the constellation Camelopardalis, in approximately 40,000 years. It will not slow down. It cannot slow down. It will pass through that star's neighbourhood and continue onward, a silent messenger from a civilization that may no longer exist. But before the silence comes, the data has arrived, and that data describes something that no Earth-based telescope, no theoretical model, no computer simulation had ever fully captured. Voyager measured the actual conditions in the space between stars, not inferred, not modelled, measured, particle by particle, field line by field line, oscillation by oscillation. What the instruments revealed was not the serene emptiness that most people picture when they imagine the void between star systems. The interstellar medium is not nothing. It is something. It has density, temperature, magnetic structure, and a radiation environment governed by the violent history of the galaxy. It presses inward against the heliosphere from all directions. It carries the fingerprints of supernovae that exploded millions of years ago. It contains particles that have been bouncing through the Milky Way for longer than our solar system has existed. And the heliosphere, the bubble that has sheltered every planet, every moon, every living cell, and every spacecraft in human history, holds all of it at bay. When Voyager crossed that boundary, it left the only protection it had ever known. It entered a realm that the sun cannot reach, cannot warm, cannot shield, and cannot control. The crossing was quiet. There was no visible flash, no audible alarm, no shudder in the spacecraft's frame. The heliopause is not a wall. It is a transition in the properties of the medium, a change in who controls the local environment. One moment the sun was in charge, the next, the galaxy was. Voyager registered the change in its particle counters, its magnetometers, and its plasma wave receiver. It noted the shift in the only language it knows, numbers transmitted as radio pulses across 15 billion miles of space, and waited patiently for someone on Earth to decode what it had found. What it found demands that we understand the structure it left behind. The heliosphere is not merely a boundary on a chart. It is a shield, a dynamic one, constantly rebuilt by the sun's continuous exhalation of charged particles. To grasp why Voyager's crossing matters so profoundly, we need to understand how that shield works, what it protects against, and why losing it changes absolutely everything about the nature of the space environment. That understanding begins with the Sun itself, with the million-degree corona that cannot hold on to its own atmosphere, and with the relentless wind that blows outward in every direction at every moment of every day. The heliosphere exists because the Sun cannot stop exhaling, and everything alive in this solar system depends on that single, continuous breath. Every second, without pause, without interruption, without any possibility of being switched off, the Sun is losing mass, not slowly, not gently. 4 million tons of matter convert into pure energy every single second through nuclear fusion in the solar core. But that is not the mass loss that concerns us here. The Sun also loses roughly 1.5 million tons of material every second through a completely different process. This material does not vanish into energy, it leaves. It physically departs the Sun's surface and races outward into space as a continuous stream of charged particles. Protons, electrons, and heavier ions, torn from the solar corona by temperatures so extreme that gravity cannot hold them, fly outward in every direction at speeds that range from 300 to 800 kilometers per second. This is the solar wind, and it is the single most important factor protecting every object in our solar system from the full hostility of the galaxy. The solar wind begins in the corona, the outermost layer of the Sun's atmosphere. The corona presents one of the most enduring puzzles in solar physics. The surface of the Sun, the photosphere, has a temperature of roughly 5,800 Kelvin. The corona, which lies above the surface, somehow reaches temperatures exceeding 1 million Kelvin. This is like walking away from a campfire and finding that the air 10 feet away is 1,000 times hotter than the flames themselves. Scientists have proposed numerous mechanisms to explain coronal heating, including magnetic reconnection events called nanoflares and the dissipation of magnetohydrodynamic waves propagating upward from the solar interior. The precise balance of processes remains an active area of research, but the consequence is settled fact. The corona is so ferociously hot that the Sun's gravity cannot contain it. At 1 million degrees and above, the thermal energy of coronal particles exceeds the gravitational binding energy at the Sun's surface. The result is an outward boiling of material that never stops. Protons and electrons, stripped from hydrogen atoms by the intense heat, stream outward in a supersonic flow. The wind is not uniform. It emerges faster from coronal holes, regions where the Sun's magnetic field lines open directly into space, and slower from regions where closed magnetic loops temporarily trap material before releasing it. The fast wind can exceed 700 kilometers per second. The slow wind averages around 300 to 400 kilometers per second. Both carry embedded magnetic field lines from the Sun, frozen into the plasma by the high electrical conductivity of the ionized material. As the Sun rotates, approximately once every 27 days at its equator, these embedded magnetic field lines get wound into a vast spiral pattern. This is called the Parker spiral, named after the physicist Eugene Parker, who predicted the existence of the solar wind in 1958, years before it was directly measured by spacecraft. The Parker spiral creates a three-dimensional magnetic structure that extends outward through the entire solar system. Every planet, every asteroid, every comet, every grain of interplanetary dust sits within this spiraling magnetic web. It is the skeleton of the heliosphere, the structural framework upon which the Sun's protective bubble is built. The wind carries this magnetic structure outward at enormous speed. At Earth's distance, 1 astronomical unit, the solar wind arrives roughly 4 days after leaving the Sun. By the time it reaches Jupiter at 5 astronomical units, it has been travelling for about 2 weeks. At Neptune's distance of 30 astronomical units, the wind has been in transit for roughly 4 months. And it keeps going, past the Kuiper belt, past the scattered disk of icy bodies, past the region where the last known large objects orbit. The wind flows onward into increasingly empty space, growing thinner as it spreads across an ever larger volume, but never fully stopping until something stops it. That something is the interstellar medium. The space between stars is not truly empty. It contains a thin but measurable population of gas and dust, threaded by a magnetic field of galactic origin. This material exerts pressure, not much pressure by any standard a human would recognize, but enough to matter over the enormous distances involved. The interstellar medium pushes inward against the heliosphere from all directions. The solar wind pushes outward. Where these two pressures balance, the heliopause forms. But the transition is not a simple boundary. It occurs in stages, and understanding those stages reveals the heliosphere's true complexity as a protective structure. The solar wind leaves the corona at supersonic speeds, meaning it travels faster than the speed at which pressure disturbances can propagate through the medium. As it flows outward, it gradually thins. The density drops with the square of the distance from the Sun. At Earth's orbit, the wind density is roughly 5 to 10 particles per cubic centimetre. By the time it reaches 30 astronomical units, at Neptune's distance, the density has dropped to roughly 1/10 of a particle per cubic centimetre. At 60 astronomical units, it is thinner still. But the wind remains supersonic, still outrunning its own pressure waves, still flowing freely outward. Then, at roughly 80 to 100 astronomical units from the Sun, depending on solar activity and the local properties of the interstellar medium, the wind hits the termination shock. This is the point where the interstellar medium's inward pressure becomes significant enough to force the solar wind to decelerate abruptly from supersonic to subsonic speed. The transition is violent in physical terms. The kinetic energy of the wind converts into thermal energy. The material heats dramatically. Temperatures in the post-shock region can exceed 100,000 Kelvin. The wind does not stop. It slows, compresses, and heats, like air piling up in front of a moving vehicle, but at a scale that spans the entire solar system. Beyond the termination shock lies the heliosheath, the thick, turbulent buffer zone where the decelerated solar wind piles up. Here, the decelerated solar wind accumulates in a turbulent, magnetically complex region that can extend 30 to 50 astronomical units farther outward. The heliosheath is where the Sun's last stand occurs. Solar material piles up, its magnetic field lines compress and fold, and the outward pressure gradually dissipates until it can no longer overcome the inward push of the interstellar medium. At the outer edge of the heliosheath, the heliopause marks the final boundary. Beyond it, the solar wind does not flow. The Sun's magnetic field does not organize the local environment. The heliosphere ends. The heliosphere is not a perfect sphere. The solar system's motion through the local interstellar medium compresses the bubble on the leading side and likely stretches it into a tail on the trailing side. Voyager 1 and Voyager 2 exited through different regions of this asymmetric structure, which partly explains why they crossed the heliopause at slightly different distances from the Sun. Now, the critical question: why does any of this matter for protection? The answer lies in what the heliosphere keeps out. The galaxy is saturated with cosmic rays. These are not electromagnetic radiation like visible light or radio waves. They are physical particles, mostly protons but also helium nuclei, heavier atomic nuclei, and electrons, travelling at velocities that approach the speed of light. The energy of individual galactic cosmic ray particles spans an extraordinary range. At the low end, cosmic rays carry energies of a few million electron volts, comparable to particles produced in medical equipment. At the high end, the most energetic cosmic rays ever detected carry energies exceeding 100 billion electron volts, concentrated into a single subatomic particle. A proton at that energy carries the kinetic energy equivalent of a professionally thrown baseball compressed into a space smaller than an atomic nucleus. These particles originate from the most violent processes in the Milky Way. Supernova remnants are the primary source. When a massive star explodes at the end of its life, The resulting shockwave expands outward through the interstellar medium at thousands of kilometers per second. This shockwave persists for thousands of years, gradually decelerating but continuously accelerating charged particles trapped in the magnetic turbulence at the shock front. A process called diffusive shock acceleration allows particles to bounce back and forth across the shock boundary, gaining energy with each crossing. Over thousands of years, this mechanism produces protons and heavier nuclei, with energies spanning many orders of magnitude, from modestly energetic to spectacularly extreme. Other sources contribute as well. Pulsars, the rapidly spinning neutron stars left behind after certain supernovae, generate intense rotating magnetic fields that can accelerate particles to high energies in their magnetospheres. Binary star systems, where material transfers between companions produce shocks and magnetic environments capable of particle acceleration, and at the larger scales, the supermassive black holes at the centers of active galaxies generate jets of relativistic plasma that produce the highest energy cosmic rays observed. Particles so energetic they may originate from other galaxies entirely and travel across millions of light-years of intergalactic space before reaching the Milky Way. The flux of galactic cosmic rays in interstellar space, as now confirmed by Voyager's measurements, is substantial. It represents a continuous rain of high-energy particles arriving from all directions, generated by violent events spread throughout the galaxy's history. Some of these particles have been traveling through the interstellar medium for millions of years, scattered and redirected by the tangled galactic magnetic field, their original source long since faded into a cold remnant or dispersed entirely. The heliosphere blocks the majority of these particles from reaching the inner solar system. The shielding mechanism is electromagnetic. Galactic cosmic rays are electrically charged. When a charged particle enters a magnetic field, it experiences a force perpendicular to both its velocity and the field direction. This force curves the particle's path. In the complex, turbulent magnetic environment of the heliosphere, incoming cosmic rays encounter a constantly shifting maze of magnetic field lines carried outward by the solar wind. Lower energy cosmic rays, which have smaller momenta and are more easily deflected, get scattered repeatedly. Their paths become randomized. Many are turned around entirely, reflected back into interstellar space before they penetrate to the inner solar system. Higher energy cosmic rays with greater momentum are harder to deflect. Some punch through the heliosphere's magnetic barrier and reach Earth's vicinity, but even these are partially moderated by the journey through the turbulent magnetic field. The effectiveness of this shielding varies with the solar cycle. During solar maximum, when the sun is most active, the solar wind is stronger, the magnetic field is more intense and more disordered, and the heliosphere inflates slightly. Cosmic ray suppression increases. The flux of galactic cosmic rays reaching the inner solar system drops measurably. During solar minimum, when the sun is quieter, the wind weakens, the magnetic field becomes more orderly and less effective at scattering particles, and more cosmic rays penetrate inward. This 11-year oscillation in cosmic ray intensity is one of the most reliably measured phenomena in space physics, tracked continuously by ground-based neutron monitors and space-based particle detectors for over 70 years. The quantitative impact of heliospheric shielding is significant. Estimates based on both modeling and direct measurement indicate that the heliosphere reduces the galactic cosmic ray flux, reaching the inner solar system by approximately 70 to 75% compared to the unshielded. Interstellar value. For lower energy cosmic rays, those below roughly 1 billion electron volts per nucleon, the suppression is even more dramatic. The heliosphere effectively excludes the vast majority of these particles, reducing their flux by factors of 10 or more. Only the most energetic galactic cosmic rays, those above roughly 10 billion electron volts, pass through the heliosphere with relatively little attenuation. This is not a minor effect. It is the difference between a radiation environment that permits complex chemistry and one that systematically destroys it. Galactic cosmic rays interact with matter in ways that are fundamentally different from the lower energy solar radiation that dominates inside the heliosphere. When a high-energy cosmic ray proton strikes an atomic nucleus in biological tissue, it does not merely ionize a few atoms along its path. It can shatter the nucleus entirely, producing a shower of secondary particles, neutrons, protons, pions, and heavier fragments that spread damage across a wide area. A single galactic cosmic ray heavy ion, such as an iron nucleus traveling at nearly the speed of light, can destroy every cell along its path through tissue. The resulting DNA damage is qualitatively different from that caused by lower energy radiation. It involves clustered lesions, multiple simultaneous breaks in the DNA double helix that are far more difficult for cellular repair mechanisms to fix. The biological consequences of chronic galactic cosmic ray exposure are a primary concern for space agencies planning missions beyond low Earth orbit. Astronauts aboard the International Space Station, which orbits within Earth's magnetosphere and well inside the heliosphere, receive a radiation dose roughly 10 times higher than the average person on Earth's surface, mostly from trapped radiation in the Van Allen belts and from the fraction of galactic cosmic rays that penetrate the heliosphere and Earth's magnetic field. Even this modest cosmic ray exposure is carefully tracked and limited by mission duration constraints. A crew travelling beyond the heliosphere would face the full, unshielded galactic cosmic ray flux. The radiation dose rates in interstellar space, based on Voyager's particle measurements extrapolated through standard radiation transport models, would substantially exceed the annual limits currently imposed on astronauts by every major space agency. Over a multi-decade interstellar transit, the cumulative dose would pose severe risks including elevated cancer rates, cardiovascular damage, cataracts, and potential central nervous system effects including cognitive decline. These are not speculative concerns. They are direct extrapolations from measured particle fluxes using well-established radiation biology. But the heliosphere's protective role extends beyond shielding biological tissue. It also protects the chemical environments on planetary surfaces and in planetary atmospheres. Consider Mars. The red planet lacks a global magnetic field and possesses only a thin atmosphere. Without the heliosphere, the full interstellar cosmic ray flux would bombard the Martian surface continuously. The increased radiation would accelerate the radiolysis of any subsurface water ice, breaking water molecules into hydrogen and oxygen through radiation-driven chemistry. It would increase the production of oxidizing compounds in the Martian soil. It would make the surface even more hostile to organic chemistry than it already is. The heliosphere does not make Mars habitable, but it reduces the radiation load on the Martian surface by a substantial margin, preserving at least the possibility of subsurface environments where liquid water might persist without being chemically destroyed by radiation. The same logic applies to the icy moons of the outer solar system. Europa, Enceladus, Titan, and other bodies with potential subsurface oceans exist within the heliosphere's protection. The cosmic ray flux at their distances from the Sun is already higher than at Earth's orbit, because the heliosphere's shielding is less effective in the outer regions. But it is still substantially lower than the full interstellar value. If these moons orbited a star with a weaker stellar wind and a smaller heliosphere, the cosmic ray bombardment of their ice shells would be more intense, potentially affecting the chemistry of their subsurface oceans over geological time. Even in the inner solar system, the heliosphere's absence would be noticeable. Earth's own magnetic field provides a second layer of protection, deflecting most charged particles that make it past the heliosphere, but the magnetosphere is not impregnable. During geomagnetic storms, when the Earth's magnetic field is disturbed by solar activity, cosmic ray access to the upper atmosphere increases temporarily. If the background cosmic ray flux were 3 to 4 times higher due to the absence of heliospheric shielding, the baseline radiation dose at Earth's surface would increase. The effect at sea level would be modest, perhaps a 10 to 20% increase, because the atmosphere provides yet another thick layer of shielding. But at aircraft altitudes, in low Earth orbit, and especially on the surface of the Moon, which lacks both atmosphere and magnetic field, the increase would be substantial. The heliosphere also mediates the interaction between the interstellar medium's magnetic field and the magnetic environments of individual planets. Inside the heliosphere, each planet's magnetosphere interacts primarily with the solar wind. The solar wind compresses the dayside magnetosphere and stretches the night side into a long magnetic tail. This interaction is dynamic but relatively well characterized after decades of study. If the heliosphere vanished and the interstellar medium's magnetic field directly impinged on planetary magnetospheres, the interaction would change in ways that are difficult to predict precisely. The interstellar field has a different orientation, a different variability pattern, and potentially different plasma properties than the solar wind. Earth's radiation belts, which are populated by particles trapped in the magnetosphere through solar wind interactions, would reconfigure. The auroral zones would shift. The shielding effectiveness of the magnetosphere itself might change. But here is the part that most people never consider, the part that transforms the heliosphere from a permanent fixture of our solar system into something far more fragile and contingent. The heliosphere has not always been the size it is today. It is not a static shell. It responds to the conditions it encounters as the solar system moves through the galaxy, and those conditions have changed dramatically over Earth's 4.5 billion year history. Right now, the Sun and its planets are passing through a region of the interstellar medium called the local interstellar cloud, a relatively warm, moderately dense patch of partially ionized gas roughly 30 light-years across. The properties of this cloud determine the external pressure pushing against the heliosphere. The density of the local interstellar cloud is approximately 0.1 to 0.3 particles per cubic centimeter, and its temperature is roughly 6,000 to 8,000 Kelvin. These are the conditions Voyager measured just outside the heliopause. They are the conditions that currently define how far the heliosphere extends. But the local interstellar cloud is not the only structure in our galactic neighborhood. The solar system is located near the edge of this cloud, and within the next few thousand to tens of thousands of years, it will likely exit into a different region. Some models suggest the Sun may enter an area of lower density material, which would allow the heliosphere to expand. Other models suggest the Sun could encounter a denser cloud, which would compress the heliosphere inward. The galactic environment is not uniform. It is patchy, clumpy, and variable. And as the solar system orbits the galactic center at 230 kilometers per second, it passes through these patches on timescales that are short compared to geological history. Scientists have found evidence that this has happened before, with measurable consequences. Studies of deep-sea sediments and Antarctic ice cores have detected anomalous concentrations of the isotope iron-60, a radioactive atom produced in supernova explosions and delivered to Earth by interstellar dust. Elevated iron-60 levels have been found in sediment layers corresponding to periods roughly 2 to 3 million years ago, and again around 7 to 8 million years ago. These deposits suggest that the solar system passed through regions of enhanced interstellar material during those epochs, potentially debris from relatively nearby supernovae that temporarily increased the density of the local interstellar medium. A denser interstellar medium would compress the heliosphere. If the external pressure increased sufficiently, the heliopause could be pushed inward from its current distance of roughly 120 astronomical units to perhaps 60 or 70 astronomical units, or even closer. At those distances, the outer planets would remain inside the heliosphere, but the shielding for the entire solar system would be reduced. The termination shock would move inward. The heliosheath would thin. The magnetic barrier that deflects lower energy cosmic rays would weaken. More galactic cosmic rays would penetrate to the inner solar system, increasing the radiation dose on every planetary surface and in every planetary atmosphere. A 2024 study published in the journal Nature Astronomy explored a more extreme scenario. Researchers modelled what would happen if the solar system encountered a particularly dense cold cloud, one with a density of roughly 1,000 to 3,000 particles per cubic centimetre, far denser than the material currently surrounding our heliosphere. Under those conditions, the heliosphere could be compressed so dramatically that it would shrink inside Earth's orbit. Our planet would be directly exposed to the interstellar medium. The galactic cosmic ray flux at Earth's surface would increase by roughly an order of magnitude. The interstellar material itself, including hydrogen, gas, and dust, would interact with Earth's magnetosphere and upper atmosphere in ways that could alter atmospheric chemistry and climate. The researchers suggested this may have actually occurred roughly 2 million years ago, correlating with geological evidence from the same period. Ice core data shows a notable increase in cosmic ray indicators during that epoch. The timing overlaps with the beginning of a series of glaciation events in Earth's recent geological history. Whether the heliospheric compression directly contributed to climate change remains debated and unconfirmed, but the physical mechanism is sound. More cosmic rays reaching the atmosphere can increase cloud nucleation, affecting cloud cover and planetary albedo. Changes in atmospheric chemistry from incoming interstellar gas could modify the greenhouse effect. The connection between heliospheric size and planetary conditions is not speculative. It is a matter of magnitudes and timescales. This variability transforms the heliosphere from a permanent feature into a conditional one. It exists because the sun produces a wind, yes, but its size and effectiveness depend on what that wind pushes against. Change the external conditions, and the shield changes with them. The protection we enjoy today is the product of a specific, temporary equilibrium between a specific stellar wind and a specific interstellar environment. Shift either variable, and the calculation changes. The solar system has orbited the galactic center roughly 20 times since the sun formed. Each orbit takes approximately 230 million years and carries us through different regions of the galactic disk. Some orbits pass through spiral arms where supernova rates are higher and the interstellar medium is denser and more turbulent. Other segments of the orbit carry us through the quieter interarm regions where conditions are calmer. The heliosphere breathes in response, expanding during quiet passages and contracting during turbulent ones. Earth's cosmic ray exposure has fluctuated accordingly, rising and falling on timescales of tens of millions of years in a rhythm dictated by our galactic orbit. Some researchers have proposed correlations between these cosmic ray fluctuations and mass extinction events in the geological record. Though these correlations remain tentative and controversial, the statistical evidence is suggestive but not definitive. What is definitive is the underlying physics. The heliosphere can change size. The cosmic ray flux at Earth can change. And the driver of that change is not anything happening within the solar system, but the conditions the solar system encounters as it moves through the galaxy. This realization adds a layer of vulnerability to the story that transforms the heliosphere from reassuring to sobering. We are not simply protected, we are conditionally protected. The heliosphere is not a fortress. It is a tent, erected by the solar wind, held up by the continuous outpouring of charged particles from the corona, and pressed upon from all sides by an interstellar medium whose properties we do not control and cannot predict with certainty. The tent holds today. It has held for billions of years, with variations, but it is shaped by its environment, and that environment is not static. None of this will happen during the sun's remaining main sequence lifetime, in the sense of the heliosphere vanishing permanently. The sun has roughly 5 billion years of hydrogen fuel remaining. As long as it burns, the solar wind will blow and the heliosphere will exist in some form. But the heliosphere is not eternal, and it is not fixed. When the sun eventually exhausts its hydrogen and evolves into a red giant, its outer layers will expand enormously. The nature of its wind will change, and when it finally sheds those layers and collapses into a white dwarf, the wind will cease. The heliosphere will dissipate. Whatever remains of the solar system will be exposed to the full interstellar medium for the first time since the sun ignited 4.5 billion years ago. Other stars face this reality on different timescales. Massive stars burn through their fuel in millions of years rather than billions. When they explode as supernovae, their heliospheres, often called astrospheres, are destroyed instantly. The planetary systems around those stars, if any existed, are suddenly exposed to the interstellar medium, while simultaneously being engulfed by the expanding supernova remnant. The radiation environment changes catastrophically. But even stars on the main sequence vary enormously in their heliospheric protection. Red dwarfs, which constitute roughly 70% of all stars in the Milky Way, are small, cool, and produce relatively weak stellar winds. Their astrospheres may be significantly smaller than the Sun's heliosphere. Some models suggest that habitable zone planets orbiting red dwarfs sit so close to their host star that they remain within the astrosphere, but the margin is thin. A particularly active phase of the interstellar medium, perhaps a passing shock from a nearby supernova, could temporarily compress the astrosphere and expose those planets to enhanced cosmic ray fluxes. This means that heliospheric protection is not a universal feature of planetary systems. It depends on the host star's mass, age, activity level, and the properties of the local interstellar medium. Some planetary systems in the galaxy may exist with heliospheres that are barely effective. Their habitable zone planets would experience cosmic ray fluxes several times higher than Earth's, with consequences for atmospheric chemistry, surface radiation, and the long-term stability of complex organic molecules. The heliosphere is not a luxury. It is infrastructure. It is the invisible architecture that makes the interior of our solar system a fundamentally different environment from the galaxy at large. Without it, the conditions that permit complex chemistry, stable atmospheres, liquid water, and biological evolution would be degraded. Not necessarily destroyed, life is remarkably resilient, but significantly compromised, and it is not permanent. It is contingent on the Sun's output, on the density of the interstellar medium we happen to be passing through, and on the galactic environment that changes beneath us like weather we cannot forecast and cannot control. And this is what makes Voyager's crossing so consequential. When Voyager 1 passed through the heliopause on August 25, 2012, it did not simply cross a line on a chart. It left the only environment in which human civilization, human biology, and human technology have ever operated. It entered a place where the sun offers nothing. No warmth, no light to speak of, no magnetic shielding, no wind to push back the cosmic rays. Voyager crossed from protection into exposure, from the conditional safety of the tent into the full force of the storm that has been raging outside for as long as the galaxy has existed. Most people, when they think about the challenges of space travel, think about distance. They think about the years it would take to reach another star, the fuel required, the loneliness of the journey. These are real challenges, but Voyager's data reveals a challenge that is in many ways more fundamental. It is not merely the distance that makes interstellar travel so daunting. It is the nature of the environment that fills that distance. The interstellar medium is not a passive void to be crossed. It is an active, irradiated, magnetically structured medium that must be endured. And enduring it requires protection that the sun can no longer provide once you leave the heliosphere. Every probe we have ever launched, every astronaut who has ever flown, every satellite that has ever orbited any planet has done so within the heliosphere. We have never operated anything outside this bubble except the 2 Voyagers, and those 2 spacecraft are the only instruments we have ever placed in that environment. When their power runs out, as it will within the next several years, we will have no presence in interstellar space at all. We will be entirely contained within the heliosphere, shielded, protected, and utterly ignorant of the conditions outside unless we build something new and send it out again. The heliosphere has been protecting this solar system for roughly 4.5 billion years. Every evolutionary step that led to complex life on Earth occurred within its shelter. Every species that has ever existed, every ecosystem that has ever functioned, every molecule of DNA that has ever replicated on this planet did so under the reduced cosmic ray flux that the heliosphere provides. We evolved inside the bubble, and until Voyager, we had no direct evidence of what conditions are like outside it. Now we do. And the measurements make clear that the heliosphere is not merely a feature of the solar system, it is the feature. the one structure that separates the relatively benign interior of our stellar neighborhood from the full, unfiltered severity of galactic space. A structure that is not permanent, not fixed, and not guaranteed to remain the size it is today. What Voyager measured when it crossed that boundary, instrument by instrument and particle by particle, changes everything. The numbers are precise, the implications are unsettling, and together they describe an environment that is far more hostile than the serene darkness most people imagine when they picture the space between stars. The moment Voyager 1 crossed the heliopause, every instrument still functioning aboard the spacecraft began telling the same story from a different angle. The particle detectors saw it, the magnetometers saw it, the plasma wave receiver saw it. Each sensor registered a distinct change in its own domain of measurement, and when those individual changes were assembled into a single coherent picture, they described an environment that no one had ever directly sampled. Not inferred from the absorption patterns of distant starlight, not modelled in a computer simulation, not estimated from theoretical equations, measured, counted, recorded, transmitted back to Earth as ones and zeros embedded in a radio signal weaker than the glow of a birthday candle seen from the distance of the moon. The data arrived slowly, at a rate of roughly 160 bits per second, the speed of a telegraph compared to modern broadband. But every bit mattered. Every number represented a direct encounter between a 1970s-era sensor and the actual material that fills the space between stars. And the numbers were not what most people would have expected. Start with the particles. Voyager 1 carries two instruments capable of detecting energetic charged particles. The Cosmic Ray Subsystem, or CRS, measures higher energy particles, those with energies above roughly 1 million electron volts. The Low Energy Charged Particle Instrument, or LECP, covers a broader range including lower energy ions and electrons. Together, these two instruments function as a particle census, counting how many charged particles of various types and energies pass through the spacecraft's vicinity during any given time interval. Inside the heliosphere, both instruments had spent decades recording a population dominated by particles of solar origin. The solar wind itself consists of relatively low-energy protons and electrons, but the termination shock and heliosheath produce higher energy particles called anomalous cosmic rays. These are atoms from the interstellar medium that drifted into the heliosphere as neutral particles, became ionized by solar ultraviolet radiation, were picked up by the solar wind's magnetic field, and then accelerated to high energies at the termination shock. They are interstellar in origin but solar in their acceleration. They carry a distinctive energy signature that marks them as products of the heliosphere's internal physics. When Voyager 1 crossed the heliopause, the anomalous cosmic ray population vanished. Not gradually, not partially. It dropped to near zero within a matter of days. This was one of the sharpest transitions in the entire crossing dataset. The anomalous cosmic rays exist only inside the heliosphere, because they require the termination shock to reach their observed energies. Outside the heliopause, the termination shock is behind you. The acceleration mechanism is gone. The particles simply are not there. Replacing them was the unmoderated population of galactic cosmic rays, arriving at intensities the spacecraft had never experienced. These particles originate from sources scattered throughout the Milky Way, primarily supernova remnants, but also pulsars, binary systems, and other energetic phenomena. They have been bouncing through the galaxy's tangled magnetic field for timescales that can reach millions of years. By the time they arrive at any given location in interstellar space, their directional information has been almost entirely scrambled. They come from everywhere at once. An isotropic rain of high-energy particles with no preferred direction and no pause. Voyager 1's CRS instrument recorded the galactic cosmic ray intensity climbing to a level roughly 2 to 3 times higher than the maximum values observed inside the heliosphere during the deepest solar minimum conditions. This is the baseline. This is what interstellar space delivers continuously. Regardless of solar activity, regardless of the 11-year cycle, regardless of anything the sun does, The heliosphere had been suppressing this flux by the substantial margins described earlier. Outside the bubble, the full galactic value arrived without apology. But the increase was not uniform across all energies. For cosmic rays in the lower energy range, below roughly 200 million electron volts per nucleon, the increase was far more dramatic. These are the particles most effectively blocked by the heliosphere's magnetic shielding. Inside the heliosphere, even during solar minimum, the flux of these lower energy galactic cosmic rays is suppressed by factors of 5 to 10 compared to interstellar values. Once Voyager crossed the heliopause, these particles appeared in abundance for the first time. The instrument registered flux levels that had never been seen during the spacecraft's entire 35-year journey through the heliosphere. This low-energy cosmic ray population matters because it represents the component most efficiently absorbed by matter. When a lower-energy cosmic ray proton strikes a material surface or passes through a spacecraft hull, it deposits its energy over a shorter distance than a higher-energy particle would. The ionization density along its track is higher. The damage per unit path length is greater. For biological tissue, lower energy cosmic rays contribute disproportionately to radiation dose precisely because they are more readily absorbed. The heliosphere's ability to exclude these particles is one of its most important protective functions. Without that exclusion, the radiation environment changes not just quantitatively, but qualitatively. The character of the radiation shifts toward a regime that is more biologically damaging per particle. The particle data also revealed something subtle but important about the transition itself. The changeover between solar-dominated and galactic-dominated particle populations did not happen with perfect simultaneity across all energy ranges. Higher energy galactic cosmic rays, which penetrate the heliosphere more easily, showed a more gradual transition. They had already been partially present inside the outer heliosheath. Lower energy particles, which are more effectively excluded by the heliosphere, showed a sharper step at the boundary. And the anomalous cosmic rays, which exist only within the heliosphere, dropped off precipitously. This energy-dependent transition profile provided independent confirmation that the heliopause is a real physical boundary, where the shielding mechanism changes, not merely a gradual thinning of solar influence. Now turn to the magnetic field. Voyager 1 carries a magnetometer, one of the most essential instruments aboard, mounted on a long boom, extending away from the spacecraft body to minimize interference from the vehicle's own magnetic signature. This instrument measures the strength and direction of the ambient magnetic field with sensitivity sufficient to detect fields of a fraction of a nanotesla. Inside the heliosphere, the magnetic field is solar in origin. It follows the Parker spiral geometry, wound into a pattern determined by the sun's rotation and the outward flow of the solar wind. The field strength at Voyager's pre-crossing location in the outer heliosheath measured roughly 0.1 to 0.2 nanotesla. The direction was consistent with the expected solar field orientation at that distance and latitude above the solar equatorial plane. After the crossing, the magnetic field did not disappear. This was itself a finding worth noting. Some early conceptions of the heliopause imagined a transition from a magnetized interior to a relatively unmagnetized exterior. The reality proved entirely different. The interstellar medium carries its own magnetic field, generated and sustained by currents flowing through the galactic plasma, compressed and shaped by shockwaves from supernovae, sculpted by the motion of stars and gas clouds through the galaxy over millions of years. This galactic magnetic field has a typical strength in the solar neighborhood of roughly 0.3 to 0.5 nanotesla, actually somewhat stronger than the exhausted solar field in the outer heliosheath. Voyager 1 measured this transition directly. The field strength increased modestly across the heliopause boundary, from roughly 0.2 nanotesla inside to roughly 0.4 to 0.5 nanotesla outside. More importantly, the field direction changed. The interstellar magnetic field in our local galactic environment runs at an angle significantly different from the solar equatorial field that dominates inside the heliosphere. Voyager's magnetometer tracked this directional shift, recording a rotation in the field vector that confirmed the spacecraft had entered a magnetically distinct domain. However, the directional transition was not as clean as many models had predicted. Theoretical work prior to the crossing had suggested that the heliopause should produce a sharp, well-defined rotation in the magnetic field direction, a clear pivot from solar to interstellar orientation. Instead, the data showed a more gradual rotation occurring over days to weeks. The field direction shifted progressively rather than flipping abruptly. This indicated that the heliopause is not a mathematical surface of zero thickness, but a finite transition layer where solar and interstellar magnetic fields intermingle. Material from both sides of the boundary coexists in this layer, creating a region of mixed magnetic character that the spacecraft traversed over a period that corresponded to a physical distance of roughly a fraction of an astronomical unit. This finding had implications for how the heliopause functions as a barrier. A sharp boundary would act more like a wall, cleanly separating interior from exterior. A gradual boundary behaves more like a membrane, allowing some mixing and exchange of material between the two regions. The magnetic data suggested that the heliopause permits limited interchange of particles and field between the heliosphere and the interstellar medium, particularly in the boundary layer itself. This partial permeability had been suspected from theoretical models, but never confirmed by direct measurement until Voyager provided the evidence. The magnetic field data also revealed ongoing variability in the interstellar medium. After crossing the heliopause, Voyager 1 did not enter a perfectly static magnetic environment. The field showed fluctuations in both strength and direction on timescales of hours to days. These fluctuations reflect turbulence in the interstellar plasma, driven by processes operating on scales much larger than the spacecraft could sample directly. The interstellar medium is not calm. It is dynamically active, stirred by shock waves from distant supernovae, by the relative motion of interstellar clouds, and by magnetohydrodynamic instabilities inherent to any conducting fluid threaded by magnetic fields. This turbulence matters because it affects how cosmic rays propagate through interstellar space. Galactic cosmic rays scatter off magnetic irregularities as they travel through the medium. The scattering rate depends on the turbulence spectrum, the distribution of magnetic fluctuations across different spatial scales. Voyager's measurements of interstellar magnetic turbulence provided the first direct constraints on this spectrum in the very local interstellar medium, data that feeds directly into models of cosmic ray transport throughout the galaxy. Voyager 2's crossing in 2018 added a dimension that its twin could not provide. As noted earlier, Voyager 2 retained something its twin had lost decades before, a functioning plasma science instrument capable of directly measuring the speed, density, temperature, and flow direction of charged particles. Where Voyager 1 had been forced to infer plasma properties indirectly through oscillation frequencies, Voyager 2 could sample the interstellar plasma with the precision of a laboratory instrument pressed against the medium itself. The difference in data quality was transformative. At the heliopause crossing, Voyager 2's PLS detected an abrupt disappearance of the outward-flowing solar wind plasma. Inside the heliosheath, the instrument had been measuring a decelerated but still flowing solar wind with a speed of roughly 100 to 150 kilometers per second and a density of approximately 0.001 particles per cubic centimeter. At the boundary, this flow ceased. The solar wind dropped to zero. In its place, the instrument detected a plasma population that was denser, hotter in terms of particle kinetic energy, and essentially stationary relative to the spacecraft. This was the interstellar plasma, material of galactic origin that had never been measured in situ by any instrument from Earth. The density measured by Voyager 2's PLS in the interstellar medium was approximately 0.05 to 0.06 electrons per cubic centimeter. This represented an increase of roughly 20 to 40 times over the solar wind density in the outer heliosheath. Context is essential here. By any terrestrial standard, this is still an extraordinarily thin medium. Earth's atmosphere at sea level contains approximately 25 quintillion particles per cubic centimetre. Even the best laboratory vacuum chambers contain trillions of particles per cubic centimetre. The interstellar medium at 0.05 particles per cubic centimetre is, by human experience, indistinguishable from perfect emptiness. But it is not emptiness. And the difference between the heliosheath's 1,000th of a particle per cubic centimetre and the interstellar medium's 500ths of a particle per cubic centimetre is physically significant. Denser plasma transmits electromagnetic disturbances differently. It supports different wave modes. It interacts more strongly with magnetic fields. It exerts more pressure. The fact that Voyager moved from a thinner medium into a denser one upon crossing the heliopause confirmed a key theoretical prediction. The interstellar medium exerts inward pressure that confines the heliosphere. The density jump at the boundary is the physical manifestation of that confinement. The temperature measurement added another piece to the portrait. Voyager 2's PLS measured the interstellar plasma temperature at approximately 30,000 to 50,000 Kelvin. This requires careful interpretation. Temperature, in plasma physics, refers to the average kinetic energy of particles. A plasma at 50,000 Kelvin contains particles moving at speeds of roughly 20 to 30 kilometers per second. This is fast by everyday standards, but slow compared to the cosmic ray particles sharing the same space, which travel at significant fractions of the speed of light. The critical nuance is that despite the high temperature, the thermal energy density of the interstellar plasma is vanishingly small because so few particles are present. You could immerse your hand in plasma at 50,000 Kelvin in the interstellar medium and feel absolutely nothing, because so few particles would actually strike your skin per second that the total energy transfer would be negligible. Temperature without density produces no perceptible heat, but the temperature is physically meaningful because it reflects the energy state of the medium. Plasma at 50,000 Kelvin has been heated by something. That something includes ancient shock waves from supernovae, turbulent dissipation of magnetic energy, and the general thermodynamic history of the local interstellar medium over millions of years. The PLS also measured a lack of significant bulk flow velocity in the interstellar plasma at the crossing point. Inside the heliosphere, everything moves outward because the solar wind imposes a radial flow. Outside, the plasma appeared nearly stationary in Voyager 2's reference frame. This was consistent with the spacecraft having entered a medium that is not being blown outward by any local star, but instead sits in a relatively quiescent state, slowly drifting through the galaxy as part of the local interstellar cloud that our solar system is currently traversing. The comparison between the two crossings revealed details that neither spacecraft could have provided alone. The two crossings sampled different parts of the heliosphere's surface. Voyager 1 passed through the upstream nose region heading northward at 122 astronomical units. Voyager 2 exited through the southern flank at 119 astronomical units, cutting through a section of the boundary angled differently to the incoming interstellar flow. The 3 astronomical unit gap between their crossing distances was the first direct evidence from 2 independent measurements that the heliopause varies in distance depending on where you cross it. But the differences went beyond geometry. The plasma conditions at the 2 crossing points were not identical. Voyager 2's direct plasma measurements showed a slightly different density and temperature profile at its crossing compared to what Voyager 1's indirect plasma wave measurements had indicated 6 years earlier at a different location. The magnetic field properties differed as well. Voyager 2 recorded a somewhat sharper magnetic transition than Voyager 1 had encountered, suggesting that the boundary's character varies along its surface. Some sections of the heliopause may be thinner and more abrupt, others may be thicker and more gradual, with more extensive mixing between solar and interstellar material. These differences are not surprising in retrospect. The heliopause is not a rigid structure. It is a dynamic boundary between 2 fluid systems, shaped by turbulence on both sides, buffeted by coronal mass ejections from within, and interstellar pressure variations from without. Expecting it to be uniform would be like expecting the surface of the ocean to be perfectly flat. The two Voyager crossings sampled two different patches of this surface and found two subtly different sets of conditions. Together, they proved that the heliopause is a complex, variable, three-dimensional structure rather than the simple spherical shell that textbook diagrams imply. The two crossings also allowed scientists to study how the heliosphere responds to solar activity changes over time. Between Voyager 1's crossing in 2012 and Voyager 2's crossing in 2018, the Sun had gone through the peak of solar cycle 24 and was descending toward the subsequent solar minimum. The heliosphere's properties had evolved accordingly. Comparing the two datasets showed how the boundary adjusts to changing solar wind conditions on timescales of years, providing a dynamic portrait that a single crossing could never have captured. Beyond the direct plasma measurements, Voyager 1's plasma wave science instrument provided a continuous record of the ambient plasma conditions through a different method. This instrument detects electromagnetic oscillations in the surrounding plasma, vibrations at frequencies determined by the local electron density. In the interstellar medium, the instrument recorded a persistent, low-frequency plasma oscillation at roughly 2 to 3 kHz. This faint signal represented the natural oscillation frequency of the interstellar plasma at its measured density, a kind of electromagnetic background tone produced by the medium itself. When NASA released an audio rendering of this signal in 2013, converting the plasma wave frequencies into the range of human hearing, the result was haunting. A thin, steady tone, almost like a sustained note on a glass harmonica, rising and falling slightly as the plasma density fluctuated. It sounded like nothing recorded on Earth or anywhere else in the solar system. It was the voice of the interstellar medium, the sound of the galaxy's own material vibrating at a frequency dictated by its physical properties. The scientific community reacted with appropriate caution, emphasizing that the audio rendering was a translation, not a literal recording of sound waves. The interstellar medium is far too thin to support acoustic vibrations in the conventional sense. What Voyager detected were oscillations in the electric field of the plasma, electromagnetic phenomena rather than mechanical pressure waves. The conversion to audio was a tool for human comprehension, not a claim that interstellar space is audible, but the underlying physics was genuine. The plasma hum is real. The interstellar medium vibrates at a characteristic frequency determined by its electron density, and Voyager's instrument detected that vibration directly. The hum proved scientifically valuable beyond its symbolic power. It provided continuous density tracking even during the long, quiet periods between solar-driven disturbances. Coronal mass ejections from the Sun occasionally send shockwaves rippling outward through the heliosphere and into the near-interstellar medium. When these shockwaves reach Voyager's location, they cause the local plasma to oscillate more intensely, producing clear spikes in the plasma wave data that allow precise density calculations. These events are dramatic but infrequent. Between them, the quiet hum provides a baseline, a continuous background measurement that reveals the ambient state of the medium without requiring any external stimulus. The hum confirmed that the interstellar plasma density remains relatively stable over the timescales Voyager has been monitoring, hovering near 0.05 to 0.1 electrons per cubic centimeter. But within that stability, the data showed modest fluctuations, gentle rises and falls in the hum's frequency that correspond to small-scale density structures in the local medium. These variations suggest that the interstellar medium in our neighborhood is not perfectly homogeneous. Density ripples exist on scales of astronomical units, driven by the same turbulent processes detected by the magnetometer. The medium breathes, subtly and slowly, in a rhythm set by forces that have nothing to do with our Sun. The persistent nature of the hum also carried a philosophical resonance that the science team did not overlook. For decades, popular imagination depicted interstellar space as silent. The void between stars was conceived as the ultimate quiet, a realm of absolute stillness where no vibration could exist because there was nothing to vibrate. Voyager proved this wrong. The interstellar medium is not silent, it hums, not loudly, not dramatically, but continuously, at a frequency that encodes its own physical identity. The space between stars has a voice, thin and faint but measurable, and Voyager was the first human instrument to hear it. Taken as a whole, the measurements from both spacecraft produce a coherent, detailed, and unprecedented portrait of the local interstellar medium. The particle environment is dominated by galactic cosmic rays arriving from all directions with a flux 2 to 3 times the highest levels ever recorded inside the heliosphere. Lower energy cosmic rays, the component most effectively excluded by heliospheric shielding, are present in abundances 5 to 10 times greater than inside the bubble. The anomalous cosmic ray population, a product of the heliosphere's internal physics, is absent. The particle census has shifted entirely from solar to galactic. The magnetic field is galactic in origin, oriented differently from the solar field, slightly stronger than the exhausted field in the outer heliosheath, and permeated by turbulent fluctuations on multiple timescales. The boundary between solar and galactic magnetic domains is not a knife edge, but a finite transition layer where the two field systems blend over a distance of a fraction of an astronomical unit. That transition layer varies in thickness and character depending on where along the heliopause you cross it, as the two Voyager crossings independently demonstrated. The plasma is denser than the material in the outer heliosphere by a factor of 20 to 40, warmer in terms of particle kinetic energy, and essentially stationary relative to the spacecraft. It hums at a characteristic frequency determined by its electron density, a frequency that serves as a continuous monitor of ambient conditions. Small-scale density fluctuations within the plasma reveal a gently turbulent medium shaped by forces that have nothing to do with our Sun. None of these conditions were fully anticipated before Voyager arrived to measure them. Models of the interstellar medium, built from decades of remote astronomical observation, had captured the broad strokes. Scientists knew the interstellar medium was thin, magnetized, and permeated by cosmic rays, but the specific values differed from many pre-crossing predictions in ways that mattered. The plasma density at the heliopause was slightly higher than several widely cited models had estimated, suggesting the local interstellar medium exerts more pressure against the heliosphere than previously calculated. The magnetic field transition was more gradual than the clean directional flip that most simulations produced, revealing a boundary layer more complex than theory had anticipated. The cosmic ray flux distribution in the lowest energy ranges, where the heliosphere's shielding is most effective, showed a steeper increase than some models predicted, meaning the heliosphere blocks even more low-energy radiation than scientists had given it credit for. And the turbulent spectrum, both magnetic and density, proved richer than many models assumed, indicating that the interstellar medium near the Sun is more dynamically active than the quiet, equilibrium state that simplified theoretical treatments often invoke. Each of these discrepancies between prediction and measurement was individually modest. None represented a dramatic failure of theory, but collectively, they demonstrated something that scientists already knew in principle but could now confirm in practice. Remote observation can constrain the possibilities. Only direct sampling can select the truth. Models of the interstellar medium, however sophisticated, are built on assumptions about conditions at a location that had never been visited. Voyager visited, and the truth, as measured truth often does, proved more complicated and more interesting than the models had suggested. The truth is not the peaceful, inert, empty void that casual language suggests when people say, the space between stars. The interstellar medium is an active environment. It is irradiated continuously by galactic cosmic rays, carrying energies that range from millions to billions of electron volts per particle. It is threaded by a magnetic field shaped by galactic scale processes operating over timescales of millions of years. It is mildly turbulent, with density and magnetic fluctuations that reflect the ongoing dynamical evolution of the gas and dust between stars. It is cold in the sense that any macroscopic object placed within it would radiate away its heat and equilibrate to temperatures just a few degrees above absolute zero. It hums at a frequency only a plasma wave detector can perceive, and it extends, with broadly similar properties, for light years in every direction. There is a tendency, when discussing the interstellar medium, to emphasize its emptiness, and it is empty by any standard that a human body would recognize. The density is so low that a cubic volume the size of Earth would contain only a few thousand tons of material, roughly the mass of a single large ship. The particles are so sparse that individual atoms may be separated by distances measured in centimeters or meters. The medium is transparent to light. You could see through it for light years without the faintest hint of haze. But this emptiness is deceptive. The medium is not inert. It is electromagnetically active. It is dynamically structured. It is bathed in a radiation field that originates from the most violent events in the galaxy. It carries the debris and energy signatures of supernovae that exploded before our solar system existed. And it presses inward against the heliosphere from every direction, continuously testing the boundary, waiting for the solar wind to weaken. Voyager 1 and Voyager 2 did not find emptiness. They found a medium. A thin one, yes. A nearly invisible one. But a medium with definable properties, measurable characteristics, and physical consequences for anything immersed within it. The instruments aboard those two aging spacecraft provided humanity with its first direct taste of the environment that fills the overwhelming majority of our galaxy. These measurements are not merely academic. Every number in the dataset, every particle count and field strength and density estimate, carries implications for the most ambitious question humans have ever asked: whether it is possible to travel between the stars. The answer to that question depends not only on how far the stars are, but on what lies between them. Voyager has now told us, in hard data, what that something is, and the implications are more sobering than the distance alone would suggest. The cosmic ray flux is unshielded and continuous. The magnetic environment is alien and turbulent. The plasma is thin but dynamically active, humming with a voice that encodes the physical state of the galaxy itself. The temperature for any passive object approaches absolute zero. The space between the heliosphere and whatever distant astrosphere might exist around the next star is not a corridor, it is an ocean. And Voyager has now measured the depth, the salinity, and the current of that ocean for the first time. But the data does not end with description. Every particle count and field measurement and density figure points toward a set of conclusions that are difficult to hear and impossible to dismiss. They concern the future of exploration, the isolation of every star system in the galaxy, and the true nature of the Milky Way as a place where the space between stars is not merely vast but actively, measurably punishing to anything that enters it. The data is in. The particle counts are recorded. The magnetic field vectors are stored in NASA's archives. The plasma densities are published in peer-reviewed journals. Voyager 1 and Voyager 2 have given humanity its first direct measurements of the interstellar medium, and those measurements now sit on hard drives in Pasadena, California, available to anyone with the curiosity to examine them. The question is no longer what exists beyond the heliosphere. The question is what it means that the answer turned out to be this harsh. Begin with the most practical implication. Any object that leaves the heliosphere must survive the interstellar medium on its own terms. There is no partial credit. There is no gradual adjustment. The solar wind drops to zero, the heliospheric magnetic shielding vanishes, the galactic cosmic ray bombardment begins immediately and does not relent. Not for a day, not for a year. Not for the centuries or millennia that any conceivable interstellar transit would require. Consider what this means for spacecraft engineering. Every vehicle humanity has ever sent into space carries a hidden assumption baked into every specification and every design margin. The radiation models presuppose the heliosphere's shielding. The thermal budgets assume proximity to a star. The power systems rely on solar energy or radioactive fuel that will be exhausted long before any interstellar crossing is complete. Remove all of these assumptions simultaneously, and you are left with a design problem that no existing spacecraft architecture can solve. Radiation shielding is the most immediate challenge. Galactic cosmic rays, as Voyager's instruments confirmed, arrive from every direction with energies spanning from millions to billions of electron volts per nucleon. The most common cosmic ray particles are protons, but the flux includes helium nuclei, carbon, oxygen, silicon, iron, and other heavy ions, all travelling at substantial fractions of the speed of light. When these particles strike a spacecraft hull, they do not simply bounce off or get absorbed cleanly. They interact with the nuclei of the shielding material, producing cascades of secondary particles. Neutrons, protons, pions, muons, and gamma rays spray inward from the impact site, sometimes depositing more total energy inside the spacecraft than the original cosmic ray would have delivered on its own. This secondary particle production is one of the cruelest facts of radiation physics. For galactic cosmic rays above certain energies, adding more aluminum shielding actually increases the dose to anything inside rather than decreasing it. The shield becomes a particle multiplier. Researchers at NASA and other agencies have studied alternative shielding materials for decades. Hydrogen-rich compounds perform better than metals because hydrogen nuclei are close in mass to incoming protons, allowing more efficient energy transfer that degrades the cosmic ray's energy without producing heavy secondary fragments. Polyethylene, water, and even liquid hydrogen have been proposed as shielding materials. The best estimates suggest that optimized hydrogen-rich shielding can reduce the galactic cosmic ray dose by roughly 30 to 50%. This is meaningful, but insufficient for a journey lasting decades. A crew exposed to even half the unshielded interstellar cosmic ray intensity for 20 or 30 years would accumulate radiation doses far exceeding the career limits established by every major space agency. The cancer risk alone would be substantial. The potential for central nervous system degradation, cardiovascular damage, and cataract formation adds further layers of concern. Active shielding concepts, using powerful superconducting magnets to generate an artificial magnetosphere around a spacecraft, have been proposed as alternatives. The idea mimics what the heliosphere does naturally, using magnetic fields to deflect incoming charged particles before they reach the hull. The physics is sound. The engineering is nightmarish. Generating a magnetic field strong enough to deflect galactic cosmic rays with energies of billions of electron volts would require superconducting coils of enormous size, carrying currents that would produce intense magnetic fields in the crew's living quarters with their own biological effects. The mass and power requirements of such a system, using any technology that currently exists or is plausibly foreseeable, would dominate the spacecraft's total mass budget, and the field would need to be sustained continuously for the entire journey, without interruption, without failure, without degradation, for decades. Energy is the next insurmountable problem. Inside the heliosphere, spacecraft can use solar panels out to roughly 5 astronomical units, beyond which the solar flux becomes too weak for practical power generation. Radioisotope thermoelectric generators extend the range much farther, as the Voyagers have demonstrated, but their power output decays steadily as the radioactive fuel decays. Plutonium-238, the isotope used in Voyager's generators, has a half-life of approximately 87.7 years. After one half-life, the power output drops by half. After 2 half-lives, it drops to a quarter. A journey to the nearest star at Voyager's current speed would last over 70,000 years. Roughly 800 half-lives of plutonium-238. The fuel would be completely exhausted within a few centuries, leaving the spacecraft without power for the overwhelming majority of the transit. Nuclear fission reactors offer higher power output and could potentially last for decades, but even fission fuel is finite. Uranium or thorium reactors would need to be designed for operational lifetimes far exceeding anything ever built on Earth, where the longest operating reactors have functioned for roughly 60 years with extensive maintenance. A reactor on an interstellar spacecraft would need to operate autonomously, without maintenance, without refueling, and without spare parts for a duration that would strain any engineering margin. The interstellar medium itself offers no alternative energy source. There is no sunlight to collect. The particle density is far too low to fuel any conceivable ram scoop or drag-based system at the speeds a spacecraft would be traveling. The magnetic field energy density is negligible. The thermal energy of the plasma, spread across such extraordinary volumes at such low density, is thermodynamically inaccessible. An interstellar spacecraft would carry every joule of energy it will ever use, from departure to arrival, with no possibility of resupply. Temperature compounds the problem. Far from any star, an unheated object in interstellar space radiates its thermal energy into the cosmic microwave background and equilibrates at a temperature of roughly 2.7 Kelvin, approximately minus 270 degrees Celsius. At this temperature, most lubricants solidify, battery electrolytes freeze, structural metals become brittle, electronic components designed for the temperature ranges encountered inside the heliosphere cease functioning. Maintaining a habitable temperature inside a spacecraft requires continuous heating, which requires continuous power, which brings the energy problem back to the foreground. Every watt spent fighting the cold is a watt unavailable for propulsion, communication, life support, or radiation shielding systems. And then there is the distance itself, made meaningful not merely by its magnitude but by the nature of the medium that fills it. The nearest star system, Alpha Centauri, lies approximately 4.3 light-years from the Sun. At Voyager, one's current velocity of roughly 17 kilometers per second, reaching Alpha Centauri would require more than 73,000 years. Even at 10% of the speed of light, a velocity far beyond any propulsion technology that currently exists or is under serious engineering development for macroscopic spacecraft, the transit would last approximately 43 years. During every one of those years, the vehicle would be immersed in the environment Voyager measured. Full cosmic ray flux, no solar power, temperatures near absolute zero, no shelter, no harbour, no possibility of rescue or resupply. 10% of light speed is itself an extraordinary velocity. It corresponds to roughly 30,000 kilometers per second, nearly 2,000 times faster than Voyager 1. Achieving this speed with a spacecraft massive enough to carry meaningful payload, let alone a human crew, would require energy inputs that dwarf any propulsion system ever built. Chemical rockets are entirely inadequate. Ion drives, solar sails, and nuclear thermal propulsion all fall short by orders of magnitude. Only concepts like nuclear pulse propulsion, antimatter engines, or laser-driven light sails even approach the theoretical capability, and none of these have progressed beyond preliminary design studies. The engineering challenges of building, testing, and operating any of these systems reliably enough for a decades-long interstellar journey remain immense. But set aside the propulsion problem entirely. Assume that some future civilization solves it. Assume they can accelerate a spacecraft to 10% of light speed and sustain that velocity for decades. They still face the interstellar medium. They still face the cosmic ray bombardment. They still face the energy deficit and the thermal hostility. The distance is not the only barrier. The medium is. This realization extends far beyond human engineering. It applies to every star system in the galaxy. The Milky Way contains somewhere between 200 billion and 400 billion stars. Each star that produces a stellar wind, which includes most stars on the main sequence, inflates its own protective bubble analogous to our heliosphere. These astrospheres vary enormously in size and effectiveness. Massive hot stars with powerful winds create large astrospheres that may extend hundreds of astronomical units. Small red dwarfs with feeble winds produce astrospheres that may barely encompass their habitable zones. Some stars, in particularly dense regions of the interstellar medium, may have astrospheres compressed to a fraction of the size our heliosphere enjoys in its relatively low-density galactic neighbourhood. But regardless of the size of any individual astrosphere, the space between those bubbles is filled with the interstellar medium, and Voyager has told us what that medium contains: galactic cosmic rays, magnetic turbulence, cold plasma, emptiness punctuated by radiation, Every star system in the galaxy is an island surrounded by this ocean. The astrospheres are harbours. The interstellar medium is the open water, and the open water is hostile. The volume of the galaxy occupied by astrospheres is vanishingly small compared to the total volume. If you could somehow inventory the entire Milky Way, adding up every stellar wind bubble around every star, the combined volume of all those protected regions would represent a tiny fraction of the galaxy's total volume. The overwhelming majority of the Milky Way, measured by volume, consists of the interstellar medium. The thin gas, the magnetic fields, the cosmic rays, the cold, the emptiness, that is what the galaxy is made of. Stars and their protective bubbles are rare exceptions, oases scattered across a desert that stretches 100,000 light-years from edge to edge. This perspective inverts the common image of the Milky Way. When people picture our galaxy, they imagine a luminous spiral of stars, dense and glittering, a cosmic city full of potential destinations. The reality is closer to a vast, dark, irradiated wilderness with tiny campfires scattered impossibly far apart. The campfires are real. The stars are there, but the wilderness between them is the dominant feature, and Voyager has measured its hostility firsthand. Every civilization that might exist in the galaxy, if any others do exist, faces the same barrier. They sit inside their own stellar bubble, shielded from the galactic environment by their own star's wind. If they look outward and dream of reaching the next star, they confront the same interstellar medium that Voyager measured, the same cosmic ray flux, the same absence of energy sources, the same thermal hostility, the same radiation-saturated void stretching light-years in every direction. The physics does not change depending on who you are or what star you orbit. The interstellar medium is the same ocean for every island. This has implications for one of the most famous questions in science. If the galaxy contains billions of potentially habitable planets, and if even a small fraction of those develop technological civilizations, where is everyone? The Fermi paradox, the tension between the apparent probability of extraterrestrial intelligence and the absence of any evidence for it, has generated dozens of proposed solutions over the decades. Some invoke the rarity of intelligence itself. Some propose self-destruction as a universal fate for technological species. Some suggest that civilizations exist but choose not to communicate. Voyager's data offers a different, more physically grounded contribution to this conversation. The interstellar medium is not a highway connecting civilizations. It is a barrier separating them. Every star system is enclosed within its protective bubble, surrounded by a medium that punishes anything that ventures into it. Crossing that medium is not merely a matter of sufficient speed or fuel. It is a matter of surviving an environment that continuously degrades, irradiates, and drains any object that enters it. The silence of the galaxy may not reflect the absence of other civilizations. It may reflect the reality that the space between civilizations is a far more formidable obstacle than distance alone suggests. Light and radio waves cross the interstellar medium with relative ease. Electromagnetic signals propagate freely through the thin plasma, attenuated by distance and slightly dispersed by the free electrons in the medium, but fundamentally capable of bridging the gaps between stars. Communication across interstellar distances is physically possible, even if the round-trip signal delay to the nearest star exceeds 8 years. But sending a physical object, a probe, or a ship requires surviving the medium rather than merely passing a signal through it. That is a categorically different challenge. The distinction between sending a signal and sending an object illuminates something important about our galaxy. The Milky Way may be a place where information can travel between star systems, but where matter effectively cannot. Civilizations might detect each other's signals across hundreds or thousands of light years while remaining permanently unable to visit each other in person. The galaxy could be full of voices and empty of visitors, full of knowledge and devoid of contact. Every civilization an island, able to see the distant campfires of others, but unable to reach them through the hostile ocean that separates every star from its neighbors. This is the terrifying truth that Voyager's measurements illuminate. Not that the spacecraft travelled far, although it did. Not that it survived for decades, although it has. The terrifying truth is the nature of what it found. The space beyond the heliosphere is not the passive emptiness of popular imagination. It is not a benign void waiting to be traversed. It is a medium that degrades what enters it, not through drama or spectacle, but through the relentless accumulation of particle impacts, thermal drain, and the complete absence of any resource that a complex system requires to sustain itself. And it fills the overwhelming majority of the galaxy. We live inside a bubble. That bubble is inflated by an average star, maintained by a continuous outpouring of charged particles, and sustained by a nuclear fusion process that has been running for 4.5 billion years and will continue for roughly 5 billion more. Inside this bubble, the radiation is manageable. The temperatures, while extreme by human standards, are moderated by solar heating. The magnetic environment is organized by the sun's field. The conditions permit the existence of complex chemistry, liquid water, atmospheric retention, and biological evolution. Outside this bubble, none of those conditions hold. The radiation is galactic in origin and unshielded. The temperature for any passive surface approaches absolute zero. The magnetic field is alien in structure and turbulent in character. The medium offers no energy, no resources, and no shelter. Everything that makes the interior of our solar system hospitable traces back to the heliosphere's ability to hold the galaxy at bay. Voyager 1 and Voyager 2 will go silent within the next several years. Their plutonium will no longer generate enough electricity to power their transmitters. The last data will arrive at the Deep Space Network, be decoded, archived, and studied, and then silence. The spacecraft will continue outward, carried by their own momentum through the interstellar medium, cooling to the ambient temperature of the cosmic microwave background, drifting through the galaxy as inert artifacts of a species that once lived on a small rocky world 26,000 light-years from the galactic center. Voyager 1 will pass through the vicinity of Gliese 445 in approximately 40,000 years. It will not stop. It cannot stop. It will drift through that star's neighborhood, perhaps passing through the outer reaches of an alien astrosphere, and continue onward. It carries a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, greetings in 55 languages, music from Bach to Chuck Berry, the sound of wind and rain and a human heartbeat, diagrams showing Earth's position relative to 14 pulsars, a cosmic address designed to remain valid for hundreds of millions of years. The record was mounted on the spacecraft's exterior. It is exposed to the full interstellar cosmic ray flux. Over tens of thousands of years, that radiation will gradually degrade the record's surface. The grooves that encode the audio will be slowly eroded by particle impacts. The images etched into the disc will blur. The gold plating will endure longer than most materials, but even gold is not immune to the steady rain of high-energy particles that Voyager's own instruments measured and reported. The message, encoded with such care and hope in 1977, will eventually become unreadable. The interstellar medium, hostile and indifferent, will erase it. But before that erasure, the data reached us. And the data describes something that should change how every person on Earth understands their place in the cosmos. We are not residents of a galaxy brimming with accessible destinations. We are inhabitants of a single protected enclave within a galaxy that is overwhelmingly composed of the hostile medium between stars. The stars themselves are distant beyond meaningful human experience. The medium between them is harsh beyond casual intuition, and the bubble that protects us is finite, maintained by a star that will not burn forever, wrapped around a solar system that occupies an infinitesimally small fraction of the Milky Way's total volume. The Voyagers did not discover aliens. They did not find wormholes or shortcuts. They did not encounter anything supernatural or inexplicable. What they found was far more unsettling than any of those fictions. They found reality, the real, measured, physically confirmed conditions that prevail in the space beyond the sun's protection. Cold, irradiated, magnetically turbulent, empty of resources, devoid of shelter, stretching for light years in every direction before the faintest warmth of another star's influence could be detected. There is something in the human spirit that looks at the night sky and sees possibility, destinations, worlds to explore, neighbours to find. This impulse is beautiful, and it is the same impulse that built the Voyager spacecraft, launched them on their impossible journey, and kept them alive for decades beyond their design life. That impulse deserves respect. It may even deserve pursuit, but it must be pursued with honesty about what lies between here and there. The galaxy is not a map with roads connecting the dots. It is an archipelago of isolated islands in an ocean of radiation and emptiness, and the ocean is wider, colder, and more punishing than most people have ever been told. Voyager went into that ocean. It tasted the water, it measured the currents, and it sent back the truth. The truth is that what lies beyond our solar system is not merely far, it is fundamentally hostile. The heliosphere is not just a boundary, it is a refuge. The sun is not just a star, it is a shield. And the terrifying truth about what Voyager found is not that it travelled farther than any human object has ever gone. It is that everything it measured on the other side confirms what the numbers always suggested, but no instrument had ever verified. The galaxy, for all its grandeur and all its billions of stars, is made mostly of the space between those stars. And that space is no place for anything that depends on warmth, shelter, or the protection of a star to survive. Voyager told us what the galaxy really is, not from a distance, not through inference, through contact, through the direct touch of instruments against the medium that fills the Milky Way. And what the galaxy really is, for anything born inside a heliosphere, is a warning written in cosmic rays and magnetic fields and cold, thin plasma humming at 3 kHz in the dark. We received the warning. Whether we heed it, or whether we find a way to answer it, is a question the Voyagers cannot help us with. Their work is nearly done. The data has been delivered. The rest belongs to the species that built them, a species that lives on one world, orbiting one star, inside one bubble, in a galaxy that stretches 100,000 light years in every direction and is filled, almost entirely, with the very thing those two small machines were the first to touch and the first to measure and the first to report back to the only home they ever knew. The sun will keep blowing its wind, the heliosphere will hold, and beyond it, the interstellar medium will continue as it has for billions of years, quiet and harsh and vast, waiting for whatever comes next with the patience of something that has nothing but time.